In the next few minutes, I'll show you what actually happens when you send a message to a language model, why it writes one word at a time where the randomness comes from, what temperature really does, the difference between top K and top P sampling, why the same prompt can give different answers, why long responses get more expensive as they grow, and why every modern model in the world makes the same fundamental trade-off between cost, latency, and quality on every single token it generates. Welcome to Concept Stack. We produce one concept a day, and each one stacks on the last, building the framework for AI together. Let's dive into inference. Last episode, we ended with a finished assistant, a base model put through supervised fine-tuning, RLHF, and some constitutional polish, sitting on a server, weights frozen, ready to answer questions. But everything we've covered so far has been about training. None of it has been about what the model actually does when you send it a message. That's inference. Inference is where every cost on your API bill comes from, every millisecond of latency you feel, and every choice that controls how creative or how deterministic the model sounds. Today we're opening up that step. Modern language models are autoregressive. That word means a single thing. The model generates exactly one token at a time. You send in a prompt, say, what is the capital of France? The model runs one full forward pass through every layer of its parameters, and the output is not a sentence. The output is a single guess for the next token. Maybe it's the word the. The model then takes its own output, appends it to the input, and runs another full forward pass. The next token might be capital, then of, then Paris. Each token is one complete pass through the model, run sequentially, because each one depends on every token before it. This is why generation feels like it streams, because it literally does. Let's zoom into one of those forward passes. Your input, a sequence of tokens, flows through the transformer layers we covered in episode 5. At the very end, the model produces a single vector. The size of that vector equals the size of the model's vocabulary, which for a model like GPT-4 is around 100,000 entries. Each entry in that vector is called a logit, a raw score. The logit for the token Paris might be 8.3. The logit for banana might be -4. These numbers are unbounded. They mean nothing in absolute terms. They only mean something relative to each other. The model's prediction is encoded in which logits are highest. To turn raw logits into something you can sample from, the model runs them through a function called softmax. Softmax does two things. It exponentiates every value, which makes them all positive. Then it divides each one by the sum of all of them, which forces them to add up to exactly 1. The result is a real probability distribution over the entire vocabulary. The token Paris might end up with probability 0.7. Lyon might get 0.05. Most of the 100,000 vocab entries get probabilities so small they're effectively 0. Now we have something we can sample from. With a probability distribution in hand, the simplest thing you can do is greedy decoding. Always pick the single highest probability token. Greedy is deterministic. The same prompt, run twice, gives you the same answer twice. It's also boring and prone to getting stuck in repetitive loops. The way models actually generate is to sample. Roll a weighted die where each token's probability is its slice of the wheel. Paris wins 70% of the time, Lyon 5%, and so on. Most of the time you get Paris, but sometimes you get something else, and that's how variety enters the output. This is the core source of randomness in language models. It's not a bug, it's the design. Temperature is the knob that controls how aggressive that sampling is. Mechanically, before softmax runs, every logit is divided by the temperature value. A temperature of 1 leaves them alone. A temperature of 2 makes the distribution flatter. High probability tokens drop, low probability tokens rise, the model becomes more random. A temperature near 0 makes the distribution sharper. The top token's probability climbs toward 1, and you get something close to greedy decoding. So in plain terms, lower temperature is more focused and predictable, better for code or factual answers. Higher temperature is more creative and surprising, better for brainstorming. Most production assistants set temperature somewhere between 0.7 and 1. Two more knobs you'll see in any inference API. Top K sampling means before you sample, throw away every token except the top K most likely. If K is 50, you sample only from the 50 most probable tokens, regardless of how the rest of the distribution looks. Top P, also called nucleus sampling, is smarter. Instead of a fixed count, it sorts tokens by probability and keeps the smallest set whose cumulative probability adds up to P, usually around 0.9. So if the top token is already at 90% probability, top P keeps just that one. If the distribution is flat across many tokens, top P keeps a wider set. Top K is a fixed cutoff. Top P is adaptive. In practice, top P plus a moderate temperature is what production systems actually use. Now we can answer the question that confuses a lot of people. Why does the same model, given the same prompt, sometimes give the same answer and sometimes wildly different ones? The first reason is what we just covered. Sampling is random by design. As long as temperature is above 0 and top P doesn't collapse to a single token, every generation is a fresh roll of the dice. But there's a second reason that's stranger. Even with temperature set to 0, you can sometimes get different outputs. That's because GPU floating point math isn't perfectly deterministic when batches are different sizes. Tiny rounding differences can flip which token barely wins. The randomness is mostly intentional. The non-determinism at temperature 0 is the universe reminding you these are physical machines. Here's a problem nobody warns you about. We said every token is one full forward pass over the entire sequence, but the sequence keeps growing. After 100 tokens, each pass processes 100. After 1,000, 1,000. That should mean each token gets more expensive than the last. The fix is the KV cache. When the transformer processes your input, every layer computes a key and a value vector for each token. That's where K and V come from. For tokens that already exist in the sequence, those vectors don't change. So instead of recomputing them every pass, the model caches them. New tokens only compute their own K and V, then attend to the cached ones. Without the cache, generation cost grows quadratically. With it, linearly. This splits inference into two phases that get billed and timed differently. The first is prefill, when the model processes your entire prompt and fills the KV cache. Prefill is parallelizable across all the input tokens, so it's fast per token, but you pay for every one. Then comes decode, the per token loop that produces the response. Decode is sequential by definition. Every new token waits for the previous one. The latency you feel as how long until the answer starts is dominated by prefill. The latency you feel as how fast it's typing is the decode loop. That's why every API charges separately for input and output tokens, and usually charges output 3 to 5 times more. They take that much longer to produce. That's the end of this concept, but each video stacks on the last. Subscribe, and we add the next layer tomorrow. So that's inference. Autoregressive generation, one token at a time, Logits and softmax, sampling, temperature, top K, top P, the KV cache that makes long generations economical, and the prefill decode split that explains your bill. We've now covered every step of how a model gets built and how it answers a single message. But we haven't talked about the limit on how big that single message can be. Every model has a context window, the maximum number of tokens it can see at once. And that one number shapes more about how AI products are designed than almost anything else. Tomorrow, context windows. Why they exist, why they're expanding, and what happens when you run out of room. Thanks for watching.